Hey guys, welcome back to another lecture video for Chem 115. In the previous lecture video, we learned about the three factors that affect an effective collision. We also looked at how we can profile the progress of a chemical reaction through the use of potential energy diagrams. In this lecture video, we will learn how to quantify the activation energy by using the Arrhenius equation. So let's go ahead and get started. And so the Irradiance Equation expresses how the rate constant K is dependent on temperature, as seen in this equation. And so if we were to calculate the rate constant at 25 degrees Celsius, because temperature is involved in this equation, if we were to calculate the rate constant at, for example, 30 degrees Celsius, it would be different. And so the Arrhenius equation can also help us quantify the activation energy, which is denoted as capital E subscript A. So looking at the pieces of the Arrhenius equation, we have capital A, which represents the frequency factor. And so it turns out that the frequency factor has the same units as the rate constant K. And so the frequency factor, you can think about it like a fudge factor that tries to take into consideration pieces of the collision theory, where the product of the orientation probability factor, or the likelihood that the reactant molecules will have the correct orientation when they collide, and the collision frequency, how frequent these reactant molecules collide. So the product of these two, P and Z, will give us the frequency factor. And so the frequency factor is being multiplied by this exponential. So this natural exponential is the inverse of ln, or natural log. And it's being raised to negative EA, which is the activation energy. Divide this by R times T. And so the value for R, it's a gas constant. However, it's the gas constant with units of energy. And so the value that we're going to be using is 8.314 joules per mole per Kelvin. Now, to lessen the confusion, we can also rewrite the unit of R as capital J over mole times Kelvin. And so the activation energy, which is once again abbreviated as capital E lowercase a or subscript a, typically has units of joules per mole when you go through the calculation. However, it is common that the value of the activation energy is going to be a large number. And so sometimes scientists like to express the activation energy in terms of kilojoules per mole. So finally, we have capital T, which is found here in the Arrhenius equation. And capital T is representing temperature, which is in units of Kelvin. And so if you guys are given temperature units in degrees Celsius or degrees Fahrenheit, you guys will have to convert that into Kelvin units before you can incorporate it into this equation. And so what drives that is the unit for the gas constant. Notice how it's in Kelvin units. And so your Kelvin units must match up between the gas constant and temperature. All right. And so what we're going to do next is we are going to learn how to expand the Arrhenius equation into what's known as the straight line plot. And so this straight line plot of the Arrhenius equation allows us to not only solve for the activation energy experimentally, but we can also determine, for example, the frequency factor. Now, to derive the straight line plot for the Arrhenius equation, what we're first going to do is we're going to take the natural log of both sides. And the reason why we're using ln is because ln is the reciprocal of this exponential e. And so I'm going to go ahead and take the natural log of the rate constant k, and that's going to equal to the natural log of the frequency factor times this by the exponential raised to the negative ea over r times t. Next, we're going to go ahead and quote-unquote distribute this natural log. We're going to apply a property of natural log that will allow us to separate the frequency factor a against the exponential term. And so to do that, when terms are being multiplied, according to the properties of natural log, they're going to be added. And so we have the natural log of a plus the natural log of the exponential raised to the negative ea over r times t. And so by expanding the natural log, this allows us to do a couple of things. One, it allows us to bring this term over to the very front of the natural log. And two, it allows us to cancel the exponential. And so the result that we get is the natural log of the rate constant k, which equals to the natural log of the frequency factor, plus negative ea over r times t. And so what I'm going to do next is I'm simply going to switch these two terms over so that we get the natural log of the rate constant k is equal to negative ea over r times t plus the natural log of a. So one last final step, I'm going to expand this fraction so that I get the natural log of k is equal to negative ea over r times this by 1 over t plus the natural log of the frequency factor a. And so this expanded form of the Arrhenius equation might not look like much to you. However, if you overlap this equation with the equation of the straight line, it gives us a powerful tool to be able to calculate, for example, the activation energy in a collected experimental data. And so if I overlap this equation with the equation of the line, y is equal to m times x plus b, much like what we did for the straight line plots for the integrated rate laws, we're going to see some trends. And so first, this is telling us that the y-axis, the identity of the y-axis, is going to be the natural log of the rate constant k. The slope, or m, is equal to negative ea over r. The identity of the x-axis is going to be the reciprocal of temperature. And the y-intercept is going to be the natural log of a. And so basically this straight line plot will allow us to, for example, determine the activation energy if we know the slope of the line. And if we know the y-intercept, we can go ahead and calculate the frequency factor without having to figure out the orientation probability factor or the collision frequency, which is going to involve a lot more calculations. Okay, and so now that we have the straight line plot of the Arrhenius equation, what we're going to do is we're going to work through an example that will allow us to calculate the activation energy through the graphical method. And so here we have our first example. We have 2 moles of dinitrogen pentoxide, and it's going to decompose to produce 4 moles of nitrogen dioxide and 1 mole of oxygen gas. And so the main question that we're trying to address here is, what is the activation energy for this reaction? And so typically when you're trying to figure out the activation energy, and if you want to do this experimentally, you need to graph or collect 2 items. So notice that the y-axis is the natural log of the rate constant. So you have to somehow collect experimental data and calculate the rate constant at each temperature. And so if you look at the x-axis, it's the reciprocal of temperature. And so whenever you're trying to figure out the activation energy, you're trying to collect the rate constant and against the temperature. And so I went ahead and just filled in some stuff here. And so what I highlighted is the original data that's collected. And so all of the other stuff that I have not yet highlighted is the follow-up steps to getting to the point where we need to get so that we can plot this on a graph and create a straight line. So that way we can calculate, the slope and then therefore calculate the activation energy. Okay. And so once again, if I were to present this to you on your exam, I'll give you the raw temperature values and the raw rate constant values. And then you yourself need to convert them into the proper values so that it can be plotted correctly on a graph. And so how would you do this? Well, if I were to give you degrees Celsius as your temperature, for you to get the reciprocal of temperature, remember temperature must be in Kelvin units. And so therefore, for all of these temperature values, you need to go ahead and add 273.15. And so basically, if you were to take 20 and if you were to add 273.15, you'll get 293.15. If you take 30 and add that by 273.15, you'll get 303.15. And the list continues. And so the next thing that you're going to do is you are going to take the temperature and you're going to take the reciprocal of it. And so to take the reciprocal, it's simply going to be 1 divided by, for example, 293.15. And so if you plug that in your calculator, it's going to be approximately 3.41 times 10 to the negative 3. And so for the next example, to take the reciprocal of the temperature, you simply need to take punch in 1 in your calculator and divide that by 303.15. And that's going to give you approximately 3.30 times 10 to the negative 3. Now, in terms of sig figs, let's see here. I'm going to put a little note. Okay, so notice how there are 5 sig figs for the temperature value in Kelvin. And so what I wrote down doesn't contain all of the significant figures. It's just rounded to 3 sig figs. But you guys should just put a note in the back of your mind that these values should have been 5 sig figs. Okay. All right. And so once you guys have converted all temperature values into the reciprocal of Kelvin, this is going to represent, I'll do this in blue, this is going to represent the values that you're going to use to plot the straight line. All right, and so if you guys recall, the natural log of k is going to represent the y-axis on your graph. So this is going to be the y-axis. And the reciprocal of temperature is going to represent the x-axis. And so this is the x-axis in your graph. And so for you guys to obtain the values for what you're going to use on the y-axis, you're simply going to use this expression as an equation, where you're going to take the natural log of 2.00 times 10 to the negative 5. And so since this contains 3 sig figs, that means that in your final answer, you should have 3 decimal places, or 3 places after the decimal. So this is going to be negative 10.819. And so we can go ahead and do the same for this second box that's not filled. We're going to take the natural log of 7.30 times 10 to the negative 5. And since, once again, there are 3 sig figs, we're going to record 3 places after the decimal. And so that's going to be negative 9.525. Okay, so I'll just put a little note over here. It says 3 decimal places. And the rest has already been filled in. And so once you've filled in this column, you guys now have all of the points that you need to plot this on a graph. And so basically, this is going to be 1 point on the graph. This is going to be another point on the graph. This is going to be another point on the graph, another point on the graph, another point on the graph. And so if you were to plot this on Excel, for example, you'll obtain a graph that looks like this, where the y-axis represents the natural log of k. And so I'll go ahead and talk about this in greater detail when we look at the Vanhoff equation. But the units for the natural log of k is unitless. So that's something that I just want to toss out over there. And so I want you guys to look at the units of k from the raw data, and notice that it is seconds to the negative 1. In other words, it's per second. And so real quick, just as a way of review, what order of reaction does this describe? So remember in characterizing, first, second, and zero order, one way to do that is by looking at the units for the rate constant k. And so since the unit is 1 per second, that's going to describe a first order reaction. Okay. If this rate constant k was molarity per second, then that would be zero order. If this rate constant k is 1 per molar per second, then that would be second order. Anyways, going back to the main point, once you guys have obtained your values for the reciprocal temperature and your values for natural log of k, you're going to go ahead and plot them. And so the natural log of k, that is unitless, and we'll talk about that a little bit later on. However, the unit for the reciprocal temperature is 1 over Kelvin. And so this is the line that we're going to get once we connect all points. And so what you want to do, now that you've graphed the Arrhenius equation using the straight line plot form, what you want to do next is determine the activation energy. And so how can we do this? How can we determine the activation energy from these numbers from this graph? Well, looking back at the straight line plot form of the Arrhenius equation, notice that the slope is equal to negative EA over R. So if we can somehow calculate the slope of the line, and since we already know R, since it's a constant, then we should be able to figure out the activation energy. Okay. So just for completion, I'm just going to go ahead and put a note that the slope, or M, is equal to negative EA over R. And so if you know the slope of the line, then you should be able to figure out the activation energy. And so since the slope M is equal to negative EA over R, I know the formula for my slope to be y2 minus y1 over x2 minus x1. And so this tells me that I just have to pick 2 points on a line. And if it's a straight line, it actually doesn't matter which point you choose. You should be able to get the same answer. But I always try to pick the first and last on a straight line. So since the axis, and this is something that's important that needs to be brought up, since the axis of this line is natural log of k and the reciprocal of temperature, then the points you guys are going to be using is the points that are highlighted or boxed in blue. You guys are not going to be using these points when you're trying to calculate the slope, because the axis for the x and y axis for the straight line is represented by natural log of k and the reciprocal of temperature. And so I'm going to go ahead and use this point as my first point, and I'm going to go ahead and use this as my second point. But once again, since this is a straight line, you guys should be able to use any of these points if it's a perfectly straight line. But in actuality, in terms of experiments, the straight line that's collected is an extrapolate. It's not so much an extrapolation. So sometimes your points are not perfectly aligned, and so what you'll get is you'll tell the computer to do a linear fit or something like that. I actually kind of drew it the other way, so it'll be like this. Right, so notice how these points are not all in a straight line, so you guys are going to tell Excel to do a linear fit. And this just comes from experimental error. Okay. And so Excel will automatically actually tell you the slope, and you guys don't really need to calculate it. But if this was on your exam, you guys will have to use you guys will need to know how to calculate the slope of a line. All right. And so let's just go ahead and fill in these numbers. So y2, I'm going to use as negative 5.843. And y1, I'm going to go ahead and use the negative 10.819. So I'm using the first point and the last point. And so this is going to be parentheses negative 10.819. And so now that I have my y values set up, I'm going to go ahead and describe the change in my x values. So since I used the last and the first point, I'm going to go ahead and use the last and the first point as well. So I have 3.00 times 10 to the negative 3 minus 3.41 times 10 to the negative 3. All right, so I'm going to go ahead and plug that into my calculator. And so what I'll get is negative 1.2 times 10 to the positive 4. Now let's go ahead and talk about units. So remember that natural log of k is unitless. And so there's really no units that goes up here. Okay, so this is unitless. And so when you look at the x-axis, it has a unit. It's the reciprocal of Kelvin. So it's 1 per Kelvin. Now, if you're dividing a fraction with another fraction, then the denominator kind of flips up. So you guys can prove this yourself by dividing two fractions. And so my final unit is just going to be Kelvin, not 1 per Kelvin. All right, so now that I have my slope is going to equal to negative EA over R. So I'm going to go ahead and put negative 1.2 times 10 to the positive 4 Kelvin equals to negative EA over R. And R is going to be 8.314 joules per mole times Kelvin. And so what I'm going to do is solve for EA by multiplying it over to the other side. And I'll do this in one go. So I'm going to multiply negative 8.314. So that way I can hit two birds with one stone. I can cancel this and I can cancel the negative, making EA positive. And so what I'll get is positive 1.0 times 10 to the positive 5. Actually, you know what? Let me just show my work here so that way you guys can see units cancel. So I'll do negative 1.2 times 10 to the positive 4 Kelvin times this by 8.314 joules, mole, and Kelvin. So notice that the Kelvin units will cancel, leaving us with, negative 8.314, leaving us with the activation energy. And multiplying these two values is going to give us a positive value of 1.0 times 10 to the positive 5. And so that's going to be joules per mole. And so if you leave this as your final answer, then that's okay. However, if the question were to ask you to express it in kilojoules, how would you do that? Well, if you guys recall, kilo is 1,000 or times 10 to the positive 3. So what you can do is I'll do this over here. So I have 1.0 times 10 to the positive 5. What you can do is you can break down this scientific notation into two terms, times 10 to the positive 2, and then times 10 to the positive 3. And so if you were to multiply these two, you're basically adding these two exponents. So 3 plus 2 is 5. And so the times 10 to the positive 3, that's the same thing as a kilo. And so what you get is 1.0 times 10 to the positive 2, since that's the only thing that remains. And then you're going to get kilojoules per mole. And so this is the answer in kilojoules per mole. This is the answer in joules per mole. You guys can also do this through prefix conversions, something that you guys have learned in first semester general chemistry, and you guys will get the same answer. So it's going to be 100 kilojoules per mole, or 1.0 times 10 to the positive 5 joules per mole. So that's great. We're able to solve for the activation energy using the data that was gathered from an experiment. And so not only do we know that this reaction is first order because of the unit of the rate constant K, we now know that the activation energy, that hill on a potential energy diagram, is going to be 1.0 times 10 to the positive 5 joules per mole, or 1.0 times 10 to the positive 2 kilojoules per mole. Cool. So hopefully this example helps you understand how to calculate the activation energy. And so you can also determine the frequency factor, capital A, if you know the Y-intercept. And so if you know the Y-intercept, or when the line hits the origin, or 0.0000 on to infinity, then you can just take the exponential of that value to get capital A. So if you were to take the exponential of both sides, this will cancel, and that'll give you the frequency factor A. And so you must know the Y-intercept. And so looking at this graph, notice that this point is not 0.00000, it's not the origin. And so this value is not the Y-intercept. And so if you guys were to plot this point on Excel, I encourage you guys to do so. If you guys were to plot this on Excel, and then program Excel such that it'll give you the equation of the best fit line. The best fit line will tell you the Y-intercept. And so all you have to do is take the exponential of the value of the Y-intercept, which is B, take this guy right here, and take the exponential of this guy to determine what the frequency factor is. All right, and so I want to go ahead and introduce you guys to another equation. And so this is known as the Vanhoff Equation. It's taking the straight line plot form of the Arrhenius Equation, and basically what Vanhoff did is just take a ratio of those two equations. It's kind of like method of initial rates, sort of, is analogous to it. But anyways, let's not worry about the proof on how to get this equation. Just know that this equation exists and know how to use this equation. And so basically, this is another way for you guys to determine the activation energy of a chemical reaction if you know the value of two rate constants and their corresponding temperature values. And so all of this data was taken from this original set. And so it's 293 Kelvin and 333.15 Kelvin. It's going to be 2.0 times 10 to the negative 5 and 2.90 times 10 to the negative 3. So I'm basically using the first and the last point. And so I'm going to go ahead and use the same kinetic data and plug it into my Vanhoff equation to see if we can get an agreeable value for the activation energy. And so basically all you have to do is plug in these numbers into this equation. And so this K2, I'll just go ahead and start writing. So if I were to take the natural log of K2, so if you look, K2 is in the numerator, so that's going to be 2.00 times 10 to the negative 3, 1 per second. And so notice that I do have a unit for the rate constant because I'm using the raw rate constant value. And so K1 is going to be 2.00 times 10 to the negative 5, 1 per second. And so if you guys recall, earlier on I mentioned this in this lecture video that the natural log of K is going to be unitless. And the reason why it's unitless is because if you take a ratio of those two, those units will cancel out. Okay, and so I'm going to go ahead and just continue writing everything else. So here I have negative EA over R. This is going to be 8.314 joules per mole times Kelvin. And so this is going to be multiplied by 1 over T2, and T2 is going to be 333.15 minus 1 over 293.15. And so since these are Kelvin units, I'm just going to put K. Let me zoom in here. I'm going to put Kelvin, and I'm going to put Kelvin. Okay. And so I simply forgot to add in the 0.15. Let me just add it right there. Okay. All right, so the first thing I'm going to do is I'm going to reduce this term. So I'm going to work inside the parentheses, and I'm going to plug that into my calculator. So I have 2.00 times 10 to the negative 3. Divide this by 2.00 times 10 to the negative 5. So that's going to give me 1.00 times 10 to the positive 2, or 100. So this is a natural log of 1.00 times 10 to the positive 2. Now when I take the natural log of that number, since I have 3 sig figs, I'm going to record 3 places after the decimal. So I'm going to go ahead and take the natural log of this answer, and I get 4.605. So 3 sig figs, 3 decimal places when I take the natural log. All right, so I'm going to now focus on what's happening inside this parentheses. And so in my calculator, I'm just going to do it in one step, but when I do it in one step, I'm going to put a whole bunch of parentheses. And so I'm going to put parentheses, parentheses, 1 divided by 333.15, end parentheses, minus, and then another parentheses, 1 divided by 293.15, end parentheses, end parentheses. And so the way that you guys are typing this in your calculator is going to be different than what I just said, depending on what your calculator is. Excuse me. So the calculator that I have is a Casio FX 300 ES Plus. All right. And so I'm going to go ahead and plug all this in, and what I get is negative 4.0957, and then there's a whole bunch of numbers, times 10 to the negative 4. All right. And so in terms of Sig Figs here, let's see here. I actually have to do this in one piece. So 1 divided by 333.15. Okay, so that's going to give me, so 1, 2, 3, 4, 4 Sig Figs. So it's going to give me Sig Figs up to here. Okay. All right. And so I'm going to bring everything else down. So this is going to equal to negative EA over 8.314 joules per mole times Kelvin, times this by negative 4.0957 times 10 to the negative 4. Now, this is going to be, in terms of the unit, it's going to be 1 per Kelvin. And so since this Kelvin is really in the denominator, it's going to cancel with this Kelvin. Okay, and so you guys can go ahead and prove that when you, multiply, keep, change, flip, they're going to cancel. And so next, what I'm going to do is I'm just going to move some terms around. So I'm going to go ahead and divide this to the other side. And then I'll go ahead and multiply this later. Okay. And so I'm going to take 4.605, and then I'm going to go ahead and divide that by negative 4.0957 times 10 to the negative 4. Okay. And so what I get is going to be negative 1.124. So I have 4 Sig Figs, that's my minimum. 1.124 times 10 to the positive 4, which is equal to negative EA over R. Okay, or I'll just put in the number 8.314. And so very similar to what we did in the previous problem, we're going to multiply both sides by negative 8.314. And so I'm going to go ahead and I'm running out of room here. So negative 1.124. And so remember, this value is unitless. Okay, because we canceled that unit at the very beginning. So this is times 10 to the positive 4 times this by 8.314 joules per mole. Actually negative, sorry. So that's going to be the activation energy. All right, so multiplying those two, I'm going to go ahead and get an activation energy of 0.9348 times 10 to the positive 5. Let me erase this part so I have room. Joules per mole. Okay. And so looking at the answer that I got, and actually I can express this in terms of kilojoules, so I'll just put a double-headed arrow. So this can be 0.9348 times 10 to the positive 2 kilojoules per mole. And so once again, I can take a positive 3 out from this number. Okay, and convert that, represent that as kilojoules. So notice that I have 0.9348 kilojoules per mole. Or really this is, if you expand this is 93.48. And so if you look at the activation energy that we calculated using slope of the line, etc., so 1.0 times 10 to the positive 2, that's the same thing as saying 100 kilojoules per mole. And so looking at both techniques, they're giving us slightly different answers, but they're not too far off. So 93.48 kilojoules, that's pretty close to 100 kilojoules per mole. Okay. So here we have, two different techniques that we're using, and the activation energy from both techniques will give us a value that's roughly the same. And I think the source of error could be the incorporation of this 0.15. I don't think I incorporated 0.15 in the reciprocal of temperature. So that might have been one source of error. So remember how there's only 3 sig figs when I'm supposed to use 5. And so that might influence the answer that we get here. All right, cool. And so that's how you guys will use the Vanhoff equation to figure out the activation energy. And so I do encourage you guys to work through more problems using this equation. Okay, so we're going to go ahead and look at one more equation using the Vanhoff equation. And so let's go ahead and read through this problem. So a reaction has an activation energy of 40 kilojoules per mole. So this already told us what the value of EA is. And so what happens to the rate if you increase the temperature from 70 degrees Celsius to 80 degrees Celsius? And so it looks like this is going to be T1, and then this is going to be T2. And so the question is asking us what's happening to the rate. So if we look at the Vanhoff equation, the natural log of K2 over K1 is equal to negative EA over R times this by 1 over T2 minus 1 over T1. Okay, so let me just confirm K2, T2, okay? All right, so if we're trying to determine, the rate, which of these rate constants are we going to solve for? Well, it didn't tell us if we're solving for K2, K1, so that must mean that we're solving for the ratio of the rate. Okay, and so whenever you're solving for K2 over K1, you're looking at the ratio of the two rate constants. All right, so let's go ahead and solve this problem. So here we have the natural log of K2 over K1. And so we have negative EA. And so notice that the EA is 40 kilojoules per mole. So there's a problem with this. And the problem is that it's expressed in kilo. So remember that R is 8. What happened here? Okay, so R is 8.314 joules per mole Kelvin. And so for you to incorporate this 40 kilojoules, you need to expand that to 40,000 joules per mole. So that way, these units will cancel. And so next, we're going to go ahead and incorporate the temperature. Now, before you guys plug in 70 here and then 80 in there, remember that the temperature is in Kelvin units. And so the first thing that we need to do is convert 70 degrees Celsius into Kelvin units by adding 273.15. So let's go ahead and quickly do that in the calculator. So 70 plus 273.15, that's going to give us 343.15 Kelvin. And so for 80 degrees Celsius, that's going to be 10 degrees more, so that's going to be 353.15 Kelvin. So now that we have incorporated those values, or now that we've incorporated or taken into consideration the Kelvin units, we're going to go ahead and plug this into the equation. So we have 1 over T2, which is going to be 353.15 minus 1 over 343.15. Great. So the only thing that's left to do is simply plug each piece into your calculator. So I'm going to do this in pieces. So I'll do the first fraction first. So 40,000, so negative 40,000. Divide that by 8.314. And so if I plug this term into my calculator, I get negative 4.811. And then this is going to be times 10 to the positive 3 per Kelvin. Or actually, no. And so once I divide both those two, this Kelvin is going to jump all the way up to the numerator. And so now I'm going to go ahead and plug this part into my calculator and see what I get. So I have 1 divided by, actually let me put parentheses here. So 1 divided by 353.15 minus 1 divided by 343.15. So what I get is negative 8.2520 times 10 to the negative 5, 1 per Kelvin. So notice that the Kelvins cancel, and the final answer becomes unitless. And it makes sense that our answer is unitless because we're taking the ratio of two rates. And so when you take the ratio of two units, they'll cancel. Like 1 per second divided by 1 per second, they're going to cancel. So it makes sense that our final answer, or this ratio, is unitless. And so we get the natural log of K2, the rate constant of the second, over K1. Okay. So now I'm going to go ahead and multiply those two values. That's negative 4.811 times 10 to the positive 3. And so what I get is 0.3970. And so to determine the ratio, I'm going to take the exponential of both sides. So I'm going to press second ln in my calculator, and then I'm going to plug in my answer. And so it looks like the ratio K2 over K1 is going to be approximately 1.49. So let's just talk about sig figs here. So since there are, since I'm using E, okay, since there are 4 decimal places, I'm going to record 4 sig figs in my answer. So 1.487, okay, is going to be my answer. And so we can go ahead and approximate my answer to 1.500. And so that way the description makes more sense. So the question is asking what happens to the rate of the reaction if you increase the temperature by 10 degrees? And so you can answer the question by saying increasing, let me zoom in here, the temperature by 10 degrees Celsius will increase the rate of reaction by 1.5. And that's it. Okay. And so the the Vanhoff equation is pretty useful. We don't have to always solve for EA. We can solve for the ratio of the rate constants, which will give us the factor that the rate of reaction will increase by. We can also, figure out what K2 is if we know K1, EA, T2, and T1. Or if we're given K2 and K1, and if we're given EA and T2, we can figure out what T1 is or something like that. And so as long as we know all of the given values except for one variable, we can go ahead and solve for it using the Vanhoff equation. All right, so that's pretty much it for this lecture video. Hopefully this gives you a better idea of how to use the Arrhenius equation to solve for the activation energy, how to create a straight line plot using the Arrhenius equation, and how to use the Vanhoff equation in a couple of different scenarios. All right, I'll see you guys in the next lecture video.